Hey, how are you? Good afternoon. How's it going? How's it going? How's it going? Not bad. Not bad. So do you guys feel like this class is harder or easier than the basic circuit theory? What do you guys think? Easier, right? Easier. Yeah, basic circuit theory requires lots of calculations, right? What do you feel? A little bit harder? Okay, fair enough. But it's okay, it's okay. Because you guys are liking the challenging stuff, right? Alright, it's time to get started. So, how was your day? Good? Not many people are here today. What is happening? What is happening? Alright, let's get started. So, last time we've learned about self-biased MOSFET stage, right? Self-biased MOSFET stage. So, in this case, if we connect the gate side with the drain side with RG resistor, this transistor configuration gives us the always on, properties of the transistor, right? Now, let us talk a little bit about the MOSFETs as current sources. Okay, I said the single transistor can be viewed as current source, right? Current source. So here, if you take a look at this configuration carefully, then as long as what is the condition? VDS greater than VGS minus B threshold. What is the condition of the transistor? What is the operation of the transistor in this case? What is that? Saturation, right? Saturations. So, what is happening if we have the saturation region? The transistor is in saturation region. Then, this transistor provide constant current regardless of VDS, right? Regardless VDS. So let us say Vx represents what? Drain voltage, right? Drain voltage. What if Vx is greater than VDS? Then this transistor will provide the constant current, right? Constant current. Is that right? So we can replace this transistor with this current source. Okay, current source. Right? So I'm talking about this region right here. So regardless of VDS, ID is constant. Is that right? So now, here's NMOS as current source. NMOS as a current source. What about here? Here's PMOS. Right, PMOS. Now, here, VDD is what? Right. So here, if VB less than VDD, then we see, so VDD is VS, VB as VG, right? So in this case, if VDD greater than VB, then this M2 transistor also provide what? The constant current, so that we can replace the transistor with a current source. Okay, so this is the first case, and second case, and third case, and fourth case. What about third case? What about third case? What is the problem of third case? So this is PMOS. So if you take a look at the source side is not defined, right? Source side is not defined, right? So here, if we plot ID versus VDS, what is going to happen? What is going to happen? So here's VG and here's VS. Is that right? So we are seeing that V of S is varying, right? Since Y is not defined. So what is going to happen? So if we plot BGS, sorry about that. BGS versus ID. It's gonna be varying, something like this. right? Since V of S is not defined. Is that right? So, do you guys believe that this transistor will work as a current source? No, of course not. Okay? Of course not. What about fourth case? So here's NMOS. Again, here, the source side is bearing. It's not defined. The V of X is not defined. Is that right? Therefore, what is going to happen? ID versus VGS. So here's VG. Shows something like this. Right? Do you guys think that this current profile is serving as a current source? No, of course not. That's why these two configurations cannot be used as current sources. Okay? Before we move on, 정성용. 김민재. Semi episode class. 나양수. Semi episode class as well. Okay. All right, let's move on. So here, let us talk about common source stage when lambda is equal to 0. Okay. So here we have a amplifier circuit. Okay. So we apply input to the gate. Is that right? And then we sense output from the drain side. Okay? So input and output are sharing. What kind of a node? Source side, right? Source side. Therefore, we say this is common source stage. Okay, common source stage. So when it comes to the small signal model, it looks like this. And you see that the gate side, the terminal is open, right? Open circuit. So now, how do we find input impedance seen from the gate side? How do we find? How do we find? Seen from gate side. We attach a test source at the gate side, right? So here's V of X, right? As a result of that, there should be some current flow here. What is this? I of X. That is equal to 0. Why? Because the gate side is an open circuit, right? Therefore, what is the R in? Infinite, yes, yes, yes. So R in is V of X over Ix. Since I of X is equal to 0, this gives us infinite, right? So here's open circuit, right? And input and output are sharing the source. That's why we say common source stage. Okay? Now, what about output impedance seen from the drain side? Again, we attach the test source at the drain side, right? Then, what is the impedance? And we attach it the test source. Since, if you take a look at this side, what is the V1? V1 is equal to 0. What about current source? Here, the value. 0. So all we have left here is this part right here. Is that right? So what is the impedance? R out is equal to R of D. Okay? Sounds good. Right? Sounds good. Oh, so here we have the answers. And the voltage gain is equal to negative Gm times Rd. Something like common emitter stage without an early effect. Okay? Without an early effect. This is very, very similar, right? So, Gm expression is proportional to mu and Cox, right? Mu and Cox. So mu and Cox depending upon what? The processing parameters, right? So it depends upon the doping and process, it will varies, okay? Oxide thickness, whatever, okay? But we can precisely control the dimension of the transistor, right? Dimension of the transistor, width and length. Is that right? So when you design a MOSFET transistor, you gotta try to omit these two effects, mu and Cox, because mu and depending upon the temperature. So if temperature varies, the environment temperature changes, then the performance of the transistor varies as well. Okay? So, again, when we design a transistor circuit, we gotta try to exclude mu and Cox effect. Okay? Alright, now let us talk about the common source stage with channel length modulations. In that case, we have a lambda which is not equal to 0, right? Which is not equal to 0. So here I'm showing you ID versus VDS, and here the lambda is non-zero in this case. So with respect to VDS, there is a slight increment of current. Okay? So therefore, we have, what is it? 1 over R naught exists. Okay? When lambda is not equal to 0. What is R naught? Output impedance, right? Output impedance. I mean genetic output impedance in the transistor due to the channel length modulations. Is it right? So here we have a R naught. So now the gain is now changed. The voltage gain now becomes negative Gm times RD in parallel with R naught. Okay? So, let me ask you, this one and this one, which one is bigger? Gm times RD versus Gm times RD in parallel with RD. So here, between these two, RD and Gm values are the same. Then which one is bigger? First one, of course. First one. Unless R naught is infinite, right? Yes. So R naught degrades the gain actually. Okay? So now, what is R in? R in still remains the same, the infinite. What about R out? R out is simply RD in parallel with R naught. Since B1 is equal to 0, and this part is also equal to 0. So all you have left here is RD, R naught, Vx, Ix. So you see that R out is equal to Vx over Ix. You see that RD in parallel with R naught. Okay? Hey teacher, this is impossible. You said R in is infinite. Physically, is it possible? Yes, you are right. It's not possible. Why not? Why not? Because the capacitor also has some impedance, right? I said the MOSFET is a capacitor, right? MOSFET is a capacitor. So here we are measuring the impedance of the capacitor, right? That is R in. So what is the R in reality? 1 over omega C. So this is in the range of mega ohm, okay, in reality. Okay, but compared to R pi, this value is at least 3 orders of magnitude higher, right? Still very high, okay, still very high. R pi was like kilo ohm range, right? That's why I'm telling you. Okay. Now, in the CS stage, there is a gain variation with channel length. Okay, channel length. So here, if you take a look at these circuit configurations, we have a what? Ideal current source. So what is the role of the ideal current source? It can boost up the output impedance, right? So here, what is the impedance of the ideal current source? R is equal to infinite, right? So I would say this is RD. Then, what is the R out? R out. What is that? What is R out? So here, what is R down? With what is R down? R not. Yes. So here, R down is R not. And R up is what? Infinite. So we see that R out is equal to R up in parallel with R down. So R infinite in parallel with R not. So what is the overall impedance? R not. Therefore, R out before was RD, RD was R not. So GM times R not. Right? So here, R naught is equal to 1 over lambda ID, or GM, 2 mu n C ox W over L I's of D. Okay? So if we plug in if we substitute these expressions, then we see that finally we have this one. Okay? And the gain, the voltage gain is proportional to square root of channel length. Okay, channel length. Okay, so if you have a long channel length, then we have higher voltage gain. Okay, I got a really precious evaluation from you guys, the midterm evaluations. There are too much calculations and too much expressions for the circuits. Why do we have to go through this? Because you will encounter more than this actually. If you work for Samsung or TSMC, whatever, or Hynix, okay, that's why you are practicing these calculations. Okay, sorry about that, but we gotta still go through all this. Okay, unfortunately. All right. So, but here's the thing. As long as you know the small signal model and what else? The large signal model, you can drive all these things. Okay? All these things. Okay? So, in that case, you can be more expert in the circuit area. So, again, I am sorry about that, but we still have to go through all these procedures. Okay? But this is not too bad, actually. Okay? So you gotta keep practicing. Okay? To be a good, circuit engineer. I don't know if you wanna go to a circuit engineer or not, but as an electrical engineer, you still have to go through this. Because this is the requirement course, right? That's why. Okay. Now, let's move on. So here, I am showing you the CS stage with current source load. Okay, current source load. So here, let us take a look at this circuit, M1 point of view. Then, what is this? Impedance, right? Impedance or source resistance. Can we say that? R's of S, right? Because this is directly connected to the source side, right? So here, and this transistor can be viewed as current source, right? So here, we can replace this transistor with current source. Okay, so here's current source. So here we can see that this transistor serves as some kind of source load, source resistance, whatever you want to say. Okay? Now, we'd like to find the small signal parameter, which is voltage gain and R out. What do we do? So here's the impedance seen from the V outside is R out. R out is equal to R up in parallel with R down. What is R up in this case? Infinite? No. Because this is non-ideal current source because we just swap. Right? Non-ideal current source. So what is the impedance seen from the drain side of M2 transistor? Which is R up. R up is equal to RO2. Yes. You are great. Yes. What is R down? The impedance seen from the drain side of M1 transistor. RO1. Is that right? So here, R out is RO1 in parallel with RO2. Okay? And the voltage gain is equal to GM1 times R out, right? R out or RD, whatever you want to say, okay? So you can replace this with RD, this whole thing, okay? And, yeah, so we can find out by looking at the small signal model. R up is RO2, R down is RO1, okay? We can analyze this circuit to find out R1 and R2, okay? I mean R down and R up. All right? Now, so I said M2 transistor is source load when it comes to M1 point of view. Okay, M1 point of view. Now, let us look at this circuit configuration a little differently. Okay, so let's say, so here, M2, let us take a look at this transistor configuration as M2 point of view. Okay, as an M2 point of view, what is M1 transistor? What is that? Also, this serves as source load, right? Source load. Okay? Of course, they will give you, I mean, this one, M1 point of view and M2 point of view will still give you the same answer when it comes to R out and what? The voltage gain. Okay, voltage gain. So here we get the same answer. Okay, so how do we get these answers? By analyzing small signal model. Okay, small signal model. Now, let us talk about CS stage with diode connected load. Okay, diode connected load. So here, let us take a look at M2 transistor. Okay, what can you say about M2 transistor? So here, M2, if you take a look at M2 transistor, that's MMOS, right? And gate and the drain side are tied, right? Tied. Then, what can you say about these configurations? What is happening? If gate and drain is tied, then what is happening? VDS, let us compare VGS minus V threshold. Which one is bigger? The first term or second term? Which one is bigger? First term, right? First term. Since VG and VD are the same level, right? Same level. That's why always BDS is greater than BGS minus B threshold. So what is happening to M2? It's always saturations, right? Always saturations. Okay. So here, this is always saturations. Therefore, M1 transistor is always saturation as well. Is that right? By KCl at here, right? So KCl has to be satisfied. Therefore, M1 is always on as well. Okay? So if we don't consider the channel length modulations, then the voltage gain becomes something like this. Okay, why? So here, what is RD? So the voltage gain for common source stage is negative GM times RD, right? What is RD here? RD is R out, right? R out is equal to what? R up in parallel with R down. What is R up here? The impedance seen from source side of the M2 transistor. What is that? 1 over GM2, right? 1 over GM2. So R up, sorry about that, R up is 1 over GM2. What is R down? What is R down? You tell me, without channel length modulations. Doggone, what is it? Infinite! Therefore, what is RD? 1 over GM2. You are a super duper genius. Great. 1 over GM2, right? Therefore, the voltage gain becomes these expressions. Negative GM1 times 1 over GM2. If these two transistors, two MOS transistors, are fabricated in the same batch, then what is happening to mu n1 and mu n2? They are equal, right? What about Cox1 and Cox2? They are also equal. Okay? But what is not changing? What is changing? The dimension that you design. Okay? So here, GM1 is equal to square root 2 mu n Cox W over L1 ID. Since ID2 and ID1, what is the relationship between these two? They are also equal. Okay? So here's GM1. GM2 is 2 mu and 2 Cox2 W over L2 ID2, right? So these cancels out, right? And also ID cancels out. Therefore, amazing thing can happen, right? So the voltage gain is expressed only in terms of W over L of each transistor. Okay? Hey teacher, what is good about these configurations? What is good? Regardless of temperature change, regardless of transistor fabrication condition, this gain remains the same because you guys designed W over L. Okay? W over L. All right? That is good. That is good. Now, what if lambda is not equal to 0? Then what is R of? R of is equal to 1 over GM2 in parallel with R2. What is R down? R down. R down is equal to R01. So we see that R out or RD that is equal to GM2 R02 R01. Okay? Therefore, the gain becomes something like this. Okay? So here, let us read this sentence after analyzing all this. So the voltage gain is lower, but it is less dependent on process parameters. Okay, process parameters. What do you mean by the voltage gain is low or low? Why? Why do we say that? Is this cascade stage? No. I said diode connected load is not cascade stage, right? Therefore, this transistor configuration is not cascade stage. Therefore, it does not give us really high voltage gain. But we can exclude, we can eliminate all the variations because the voltage gain is only ratio between W over L between M1 and M2 transistors. Okay? Sounds good, right? Sounds good. Oh. Anyway, did I say diode connected load? Yes, indeed, it is diode connected load. Why? Because in small signal model, what do we do with the VDD? We short, right? Therefore, we can see that VG and VD are grounded, right? Therefore, okay? Do you want me to explain why? Again? All right, fair enough. So here, we have a G drain source and we want to find out R. Okay? Then what do we have to do? We're gonna make small signal model. So here gate and drain are tight. And here we have GM V1 in order to find the R out. So let's say this is R out. Okay? What do? We attach a test source, right? So here's Vx, here's Ix. So what is Ix by KCL here? KCL. I's of x is negative GM V1. Is that right? Then, what is Vx expressions? Dog one? Minus. Yes, yes, yes. So by KVL here, V1 is equal to, negative V1 is equal to Vx. So R out is equal to Vx over Ix, which is negative V1, negative GM V1. So what is the impedance? 1 over GM. Is this 3-terminal device or 2-terminal device? If you take a look at the small signal model, is it 2-terminal device or 3-terminal device? 2-terminal device rather than 3-terminal device, since we are tying gate and the drain, right? So here, so let us take a look at, this is our out. So let's say here's source side, here's drain side. Okay, the impedance seen from source side has to be equal to impedance seen from drain side. Is that right? Understood? Right? So here's RD, RS. R out is equal to RS, RD. No matter where you see, you get the same impedance for diode connected load. Is it low value or high value? 1 over GM. Very low. Okay, very low. Okay. Unlike diode at the source load, what if we connect the cascode stage? We will have much higher output impedance, so that we can boost up what? The voltage gain, as well as reduce what? The one? Reduce some kind of effect, right? What is it? Oh, okay. So if we use cascade stage, what is the benefit of using cascade stage? Yes, high AV, what else? We can eliminate what? Headroom trade-off, right? Headroom trade-off. Okay. And also, we use cascade stage instead of physical resistance. Why? In terms of the dimension of the device, for example, transistor and resistor, which one is smaller? Transistor, that's why. Okay? That's why. So in VLSI technology, okay, it is more recommended to use solely transistors rather than mixture of transistor and resistor. Okay, that's why. Okay. What else? So now, let us talk about CS stage with diode connected PMOS load. Okay, so here the lambda is not equal to 0, and what do we have to find? Oh, we want to find the voltage gain and R out. This procedure is also very similar to the previous one. So here's source, gate, drain. What can you see? Here, M1 transistor. What kind of a connection is this? The gate and drain are connected with what? The ground. What is this? So gate and drain are tied. So we can say this is also diode connected load. Then what is R down? R down is equal to 1 over GM1 in parallel with R01. What is R02? Not R02, R up. R up is impedance seen from the drain side, which is RO2. So R out is equal to R up again, R down. So 1 over GM1, RO1, RO2. Okay, so we can just plug in here as RD, right? So this R out is equal to RD. Okay, so we can view this whole thing as RD, right? That's why. What do you see here? Now, it is the time to talk about CS stage with degenerations. Okay, so here we have amplifier circuit, and here we have a RS resistor. What is RS resistor?